Yeah, good morning, all of you. Today we are going to see an important chapter, which is a Carnot engine, and we are going to. It is a completely theoretical reversible engine, just to calculate what is going to be the maximum efficiency which can be produced by using a work engine or a heat engine. Okay, so in the Carnot engine efficiency, it is a theoretical maximum efficiency we can get when a heat engine is operating between two temperatures. Okay, so as we all know, the higher temperature reservoir operating will be at a temperature TH, T suffix H, and the lower temperature of the reservoir will be at the temperature cold, T cold. Okay, so here we can divide this reversible Carnot engine by four steps. First one is going to be the isothermal expansion, then adiabatic expansion of the gas, and then the third one is going to be isothermal compression, and finally fourth step is going to be adiabatic compression. So we are going to see the steps and how the efficiency of Carnot cycle is calculated step by step. So first one is the isothermal expansion. Here we know that in isothermal expansion the temperature is going to be constant. So here what is the consideration? An ideal gas is placed in a cylinder, and it is heated by using a reservoir, heat reservoir, which is maintained at a temperature at T1. Okay, so when we are placing the reservoir near to the cylinder, what happens? The gas molecules get heated up, and the cylinder is having a piston on the top, and the piston starts moving because of the expansion of the gas. So this is an isothermal expansion, and hence the temperature will remain the same, but the pressure and the volume changes from P1 to P2, and volume changes to V1 to V2. And we know that at isothermal expansion, as the temperature is the same, as per the first law of thermodynamics, the heat energy Q will be equal to internal energy plus work done, and the internal energy is completely zero at constant temperature, and therefore the equation becomes Q is equal to W. Okay, so work done will be completely equal to the heat absorbed by the gas. Okay, so we have already derived the equation for work done in isothermal expansion. So here we are writing down the work done as 2.303 N into R into T1, because here the temperature in this isothermal expansion is T1, which is maintained in the same temperature T1, and the volume is going to be log of V2 by V1. Okay, second step is the adiabatic expansion. So in adiabatic expansion, the cylinder, actually the gas placed in the cylinder, we were providing heat for that. Now the heat reservoir is removed, and the walls are going to be insulated to calculate what is going to be the adiabatic expansion. So as the walls are automatically insulated, now no heat energy is either transferred outside or let inside. Therefore, Q will be equal to 0, and the gas expands from P2 to P3, and the volume changes from V2 to V3, and the temperature cools down from T1 to T2 because of gas expands due to heat, and now we have removed the heat reservoir. Therefore, the temperature cools down from temperature T1 to T2 adiabatically. And now the work done equation for a gas which is at adiabatic expansion can be written as W2 is equal to N into R divided by 1 minus gamma into T2 minus T1. Okay, T2 minus T1. This is going to be the work done by the gas in adiabatic expansion. Now we'll go to the third one. The third step is going to be isothermal compression. Isothermal compression. So isothermal compression, we are again the insulation which is surrounding the cylinder is going to be removed, and we are going to provide a heat sink near the cylinder, and the pressure changes from P3 to P4, V3 to V4, the volume changes, and the temperature is going to remain the constant as it is going to be an isothermal compression, and the compression is going to be provided by an external source. Okay, so now the work done can be written as 2.303 N into R into T2, that is going to be the temperature maintained here, into log of V4 by V3, V4 by V3. Okay, and finally again as it is a reversible theoretical explanation of a Carnot cycle, we are going to go to the system is going to reach the initial temperature and initial pressure and volume. Okay, so for that we have to move to the adiabatic compression. From here the pressure P4, it is moving to P1, the initial pressure, and the volume V4 is moving to the initial volume V1, and the temperature is moving to the initial temperature T1. Okay, it's because the gas is going to be compressed adiabatically, and the work done equation is given by N into R divided by 1 minus gamma multiplied by T2 minus T1, but here the final temperature is T1. Therefore, we substitute here T1 minus T2. This is going to be the pressure and volume curve for adiabatic process. It starts from A, it moves to B through isothermal compression, then from B to C in adiabatic expansion, then C to D in isothermal compression, and D to A in adiabatic compression. Okay, so this is going to be the pressure and volume changes in each and every step. Step by step, the pressure and volume is mentioned here. It is a pressure volume graph for the Carnot cycle. Now we are going to see what is the net work done by all the 4 cycles. We have to add all the 4 work dones, and W2 is opposite to W4. Isothermal expansion and isothermal compression completely cancels out because the term is a completely opposite to each other. Okay, because you can see here. So here it is going to be the adiabatic compression is given by N into R 1 minus gamma T1 minus T2. Sorry, adiabatic compression and expansion totally cancels out. Adiabatic expansion, it is given as N by NR by 1 minus gamma T2 minus T1. Okay, so finally it was due to compression it was T1 minus T2. So if we replace this term as T1 minus T2, automatically this will become a negative sign here, and therefore W2 and W4 will get cancelled. They are opposite to each other. Now we can write down the work done, net work done, by adding down the work done by the isothermal expansion and work done by the isothermal compression. Okay, so now we are going to finally find out the efficiency of the Carnot cycle. Efficiency is given by work done by the heat extracted by the heat reservoir. Okay, so this is the efficiency of the Carnot cycle, which is given by net work done divided by the Q1. Q1 is the heat provided by the reservoir. We also know that this Q1 is equal to W1 because in isothermal expansion we saw that because of no internal energy, the total heat energy absorbed is given as a work. Therefore, Q1 can be replaced by W1 and we can rewrite the equation in this form. Now we can cancel out these two terms and write down 1 plus the remaining constant terms get cancelled, and we can write down T2 by T1 log of V3 by V4 divided by log of V2 by V1. Now this is the equation number 1. Now we can see here we are going to find the efficiency of a Carnot cycle heat engine, and here if we remove the log terms, then the expression of efficiency will be in terms of temperature. Okay, so now we are going to try find out what is the relationship between these two terms, log of V4 by V3 and V2 by V1. So we can see here by using Boyle's law, the pressure and volume can be equated as P1 V1 is equal to P2 V2 for isothermal expansion, and for adiabatic expansion it is P2 V2 power gamma is equal to P3 V3 power gamma, and for isothermal compression it is P3 V3 is equal to P4 V4. For adiabatic compression it is P4 V4 power gamma, which is equal to P1 V1 power gamma. Now multiply these terms in the right hand side and the left hand side to find get the expression as V1 V3 is equal to V2 V4. V1 V3 is equal to V2 V4, and from this expression we can write down V3 by V4 can be equal to V2 by V1. Okay, so but the efficiency expression whatever we got, it is V4 by V3 in the numerator and V2 by V1 in the denominator. So what can I do now to equate these two volumes? I can change this V4 by V3 into V3 by V4. Therefore it will add up a negative sign in the end here. Okay, so I am changing V4 by V3 to V3 by V4, and therefore a negative, the positive sign is changed into negative because we know that log of 1 by A is equal to minus log A. Okay, so now we can write down, now after writing down like this, we know that these two terms are equal, these two volumes are equal, and we can cancel out the log terms and write down the efficiency of the Carnot engine as 1 minus T2 by T1. Initial temperature is at the denominator and the final temperature is at the numerator. 1 minus T2 by T1. Otherwise we can also write down efficiency eta is equal to 1 minus the temperature at the heat sink, that is Tc, divided by temperature by the heat reservoir, which is the input heat, which is Th. Okay, we can write down in that way. So next class we will be seeing the NCERT problems of Carnot engine.